Okay, so in this video, we're going to cover using arrow notation. So what you see here is the graph of some rational function. Right? For now, I won't be too caught up into what the equation of this is. Okay? So I want to use arrow notation, which we've used before in dealing with the end behavior of polynomials, right? That as x goes to infinity, f of x goes to a certain value. So we're going to use that here to describe what's called local behavior. Right, as we see here, our graph has some local behavior here, right? Apart from the x-intercepts, we have these asymptotes right here, right? These kind of vertical lines that the graph doesn't cross, right? And we also have this just hole in the graph here. Now, one thing I do want to make clear here is that at these values, f of 4, f of -1, and then f of 2, f is undefined. Okay, but that is not the behavior that I seek to describe. Right here, I can see from the graph that it's undefined. Right? What I want to take from the graph is what is happening near these values. Right, so that's kind of what the goal of arrow notation here. Right, what happens near these values. Okay, and then here at this point, near, right, could have any meaning, but especially when we're talking about, a real valued function, right? If we think of a value here, for instance, near 2, well, whatever value that I choose, I can always get closer, right? If we're on this side, we could say, oh, what about 2.01? Well, what about 2.001? And then 2.0001? Right? So we define close, we just say as we get closer, right? We know that we can always get closer. Right? Kind of an interesting thing about these real numbers, right? If you pick a number really close to 2, I can pick an even closer number. All right, and we can play this game forever. All right, so near is just kind of like, all right, what happens as I get closer and closer? And I want to seek a way to kind of describe these values, right? Now what happens at those values? I know how to describe those, right? I just call those undefined. Okay, now previously when we were talking about when we're working with polynomials, we have a way to describe end behavior. Now that still applies here, right? And let's start with that, right? The arrow notation. What happens as x goes to infinity? Now when dealing with polynomials, it was either it went to positive infinity or negative infinity. Here, we have this, what's called a horizontal asymptote, where it looks like it kind of plateaus. Right, so in this case, it kind of tapers off, and it looks like it is getting near this value of 1. Right, so you could say, all right, as x goes to infinity, right, f of x approaches 1. Not that it equals 1, right? In some cases, it might, right? It might cross this horizontal asymptote, but here, as we get further and further, it just kind of, almost like it's really, really close, right? Now, how close? Right? Really, really close, we'll say at this one. We won't put any formal language to that, right? We'll just say it gets really close. And it does the same thing on the other side, right? As we see here, right? Well, as x goes to negative infinity, f of x, let's use these double arrows. All right. I'm sorry, here. As x goes to infinity, f of x goes to 1. As x goes to negative infinity, f of x approaches 1. Excuse my sloppiness here. Okay, f of x goes to 1. All right. Okay. All right. So now let's look at our vertical asymptotes, right? How are we going to describe those? Okay, so what I'm going to use is this notation where I'm going to look at what happens on what I'm going to call the right side and the left side of my values. Okay, so instance for here, as x approaches -1, I'm going to be very specific, right? As x approaches -1, right? I want to specify, well, from which side am I coming from here? Am I coming from the right side or the left side? If I'm approaching from the left side, I'll do this one first. I'm going to use almost like an exponent of a negative side, right? We'll use that to be approaching x. X approaches -1 from the left. Okay. All right. And I want to figure out what happens to the function f of x. All right. Okay, so as we see here, as x approaches -1, again, right, getting close to, well, how close? Really, really close, right? And we can start to see the behavior that is happening here, right? As x approaches -1, right, the closer and closer I get, the further down this is going, right? That's what that arrow is indicating, right? It's just going further and further down, right? In other words, it's getting larger in the negative direction without bound. It just kind of falls off down in that direction. And the way we describe that, similar to our end behavior, is, well, that is going towards negative infinity. All right. And again, that only describes the behavior coming from the left side. I'm not necessarily guaranteed to have the same behavior on the right side. Right. And we see here as x approaches -1, and again, I'll use this little plus exponent, approaches from the right side. All right, and then we could see here again, now I'm changing my perspective here as I'm going from right, and we could see that, oh, this has a very similar behavior. And it's not guaranteed to have a similar behavior. In this case, it does, right? It gets larger and larger in the negative direction. So similar to our left-sided limit, our function here also goes to negative infinity. All right, and that's how we would use arrow notation to describe some local behavior, right? As x approaches 1 here again from the left and on the right side. So now let's take a look at our next asymptote here. Okay, and then here we have, all right, so here we see we're looking at what happens as x approaches 2, in this case positive 2, from the left side, right? So here from the left side, and again we see here close. The closer we get to 2, the further we go down in the negative direction, right? So it kind of grows without bound in the negative direction. So as x approaches 2 from the left, f of x approaches negative infinity. All right, so now let's change our approach here. Let's approach it from the right side. As x approaches 2 from the right side. And we can see, all right, as x approaches 2 from the right side. Now in this case, we have different behavior, right? As I get closer to 2, this kind of shoots up, and it goes without bound in the positive direction, right? So it gets, the closer I get to 2, the higher it goes, right? And it goes closer I get, larger values for f of x, right? So in this case, f of x goes to infinity. All right, now notice here from the right side, as x approaches 2, f of x approaches infinity. All right, so again, we're not necessarily guaranteed to have same behavior on either side of the asymptote. Sometimes we do, right? When we do have the same behavior, like for instance here, right? One thing we can say, if we have the same behavior, we can make the statement as x approaches -1, f of x approaches negative infinity. And I don't need to make the distinction from right or left. This is implied here, that it's from both sides that it approaches negative infinity. All right, so just keep that in mind here, okay? I cannot make that same statement for x approaches 2 because if one direction goes to negative infinity, or one side goes to negative infinity, the other side goes to positive infinity, okay? So just keep that in mind. All right, now, last thing here to describe our arrow notation is this hole in my graph, right? Now here I didn't make it clear here. Let's call this value here. Let's call it 1.5. All right. Not to scale, so but we'll just call it 1.5 to make things easy here. Okay, so again, I know at f of 4 it's undefined, but that's not what I'm after to describe here, right? So what I want to describe here is what happens as x approaches 4, and again, let's look at the left side first. Now here we have a different type of behavior than in our previous examples. So here I'm on the left side, so I'm like almost like, think of it like a roller coaster. What is happening here? Well, I don't get any of these going off into larger and larger values. This actually looks to be approaching a finite value. In this case, something we call the 1.5. Right, so as x approaches 4 from the negative side, from the left side, f of x approaches 1.5. Okay, so now let's change our perspective here. Let's look at the right side. All right, what happens as x approaches 4 from the right side? All right, again, we don't get these grows without bound in either direction. It's approaching this finite value of 1/2. F of x is approaching 1/2, right? Now, again, this is saying something very different than f of 4, right? Again, I want to make this point clear, right? It's a big kind of a topic in calculus when we talk about these limits, right? I know what the function value is. That is undefined. This is not what this is describing, right? It's not describing the function value, right? Because I know f of 4 is undefined, but values that are near 4 are approaching this value, f of 1.5. And again, since we have similar behavior on the left and the right, the statement we can make now is that as x approaches 4, f of 4, or f of x, I should say, approaches 1.5. Okay? All right, because the left and the right sided are approaching the same value. Okay? All right, so that's how we use our arrow notation in context with our rational functions, right, to describe local behavior that's around an asymptote or a hole, but also for our end behavior, similar to how we did when we were working with polynomials.